Today we'll take a closer look at how the Hugo robotic-assisted surgery system is physically built. The architecture is designed around flexibility. Instead of one fixed base, Hugo uses modular arm carts, a vision tower, and an open console. Each unit plays a distinct role. The arm cart provides dexterity, the tower houses computing and visualization systems, and the console connects surgeon intent to machine precision. This modularity makes the system easier to transport, position, and service. Hospitals can reconfigure operating rooms more freely, while engineers can maintain or upgrade individual components without dismantling the whole setup. In this walkthrough, we'll explore how each module fits into the larger ecosystem. We'll look at the design logic behind movable arms, compact towers, and open interfaces, all carefully engineered to balance stability, safety, and adaptability. Think of this as a guided tour through the hardware body of Hugo, the skeleton that supports its digital brain. Hugo's modular design reflects a shift in surgical robotics philosophy, from centralized systems to flexible distributed architectures. By separating the major functions into modules, the arm carts, the tower, and the surgeon console, Medtronic created a system that adapts to different procedures and operating room layouts. Each arm cart has its own motors and sensors, controlled locally but coordinated through the tower. The console, meanwhile, can be positioned wherever the surgeon prefers, improving ergonomics and communication with the team. This approach also simplifies maintenance. If one module requires servicing, others can remain operational. It's like replacing a single limb instead of operating on the whole body. Modularity encourages innovation too. New tools, imaging systems, or AI software can integrate through a standardized interfaces without redesigning the entire platform. The result is a robotic system that feels less like a rigid monolith and more like a living ecosystem, configurable, scalable, and ready for the next decade of surgical technology. The Hugo system is built like a small, coordinated orchestra, 3 main sections working in harmony. The robotic arm carts form the front line. They're positioned around the patient, each performing precise movements based on surgeon input. Behind them sits the tower, the system's central conductor, managing power, data, and visualization. It connects everything through protected cables and internal hubs. Off to the side, the open console allows the surgeon to operate with full visibility and freedom of movement. The overall layout was designed to fit within existing operating rooms by allowing each cart and console to move independently. Hospitals can tailor placement for specific procedures or surgeon preferences. This flexibility is crucial. It keeps workflow fluid, ensures clean cable routing, and gives biomedical teams faster access for troubleshooting. Together, the carts, the tower, and the console form a modular ecosystem where hardware design directly supports clinical efficiency. Each of Hugo's arm carts is an independent robotic module. Think of them as mechanical limbs, each with its own motors, sensors, and control circuits. The arms feature multiple joints, giving surgeons a range of motion comparable to a human shoulder, elbow, and wrist combined. High-precision actuators deliver smooth movement, while encoders provide real-time position feedback. The base of each cart includes wheels and locking casters. This allows the team to move arms around the table, adjust positions between cases, or dock them for maintenance. Height adjustable columns align instruments with the surgical field without obstructing assistance. Inside, energy and data are managed through secure connectors routed up the arm, keeping the external layout uncluttered. This mobility transforms the OR instead of the patient adapting to the robot. The robot adapts to the patient. It's a small but powerful reversal in design philosophy, one that defines Hugo's hardware identity. The tower is Hugo's central nervous system, a vertical unit that links every moving and thinking part of the system. Inside the tower are computing modules that coordinate the robotic arms in real time. It also routes video signals from cameras to the surgeon's console, synchronizing multiple data streams with minimal latency. Power management happens here too. The tower distributes energy safely across all modules and integrates with the hospital's electrosurgical units, like the Valley Lab generators. Externally, it serves as a docking hub. Each arm cart and the console connect through labeled ports. Maintenance engineers can access internal components through service panels, simplifying upgrades or part replacement. The compact footprint is deliberate. The tower must fit through standard OR doors and move easily between rooms. In essence, the tower is a conductor of Hugo's hardware orchestra, silent but crucial, ensuring that energy, data, and precision flow without interruption. The surgeon's console. This is where the human intuition meets robotic precision. It's designed to be open, no enclosed cabin, so the surgeon can stay connected with the OR team. This is more than convenience, it's safety and collaboration by design. The console features a high-definition 3D monitor that recreates depth perception, helping the surgeon navigate delicate structures. Hand controllers translate natural wrist and finger movements into scaled robotic motions. Foot pedals manage camera zoom, clutch control, and instrument activation, keeping workflow smooth. A clever safety feature is the head tracking sensor. When the surgeon looks away from the console, all instrument movement pauses automatically. Every detail, from posture alignment to touch sensitivity, was engineered to reduce fatigue and improve precision during long procedures. The open console approach reinforces Hugo's modular spirit, flexible, communicative, and ergonomically tuned to human performance. Docking may seem like a small detail, but in robotics it defines the entire workflow. Hugo's arm carts can be arranged in several configurations, depending on the surgical site and patient positioning. In a compact layout, the arms cluster closely for confined spaces, but the butterfly arrangement spreads arms diagonally for better range during multi-quadrant procedures. Bridge or straight setups optimize access for colorectal and gynecologic cases. Each cart includes mechanical alignment cues and software-guided positioning to reduce setup time. Once docked, the system verifies communication and geometry before operation. The design balances proximity and safety. Arms must reach precisely without colliding or crowding assistance. Docking flexibility also future-proofs the platform. Different specialties can customize setups without new hardware. In short, modular docking transforms Hugo from a static machine into a configurable surgical partner, adapting to the room, the surgeon, and the patient. Behind every smooth robotic motion is a well-planned power and data network. Hugo's infrastructure was designed for reliability and safety. The tower houses the primary power management system. It uses isolation transformers and circuit protection to meet strict medical standards. Power and data are distributed to each arm cart and the console through durable color-coded cables, routed beneath the floor or along defined channels. Each connector is keyed to prevent incorrect attachments. a small but vital safeguard during quick turnarounds between cases. An uninterruptible power supply provides enough backup energy to safely complete or pause a procedure during brief power distributions. Cable organizations also improve workflow. No cluttered floor, fewer trip hazards, and faster cleaning cycles. The takeaway is that even though power systems aren't visible during surgery, their design quietly upholds everything else: stability, precision, and safety in every motion Hugo makes. Cooling and maintenance are often overlooked, yet they determine how long a system stays reliable. Hugo's components generate significant heat during prolonged operations, especially within the tower and arm joints. Engineers solve this through intelligent airflow design, strategically place fans and ducts that direct air over critical components while keeping the noise low. Serviceability was equally important. Removable panels and modular hardware assemblies allow technicians to replace parts without dismantling the entire cart. Filters are positioned at the edge of airflow paths for easy cleaning or replacement, keeping internal electronics dust-free. Diagnostic ports provide live system data, letting engineers check temperature, voltage, and motor performance in real time. Every maintenance choice connects to the bigger goal: maximizing uptime and minimizing disruption in the surgical schedule. In practice, this means surgeons see fewer delays and hospitals spend less time troubleshooting, all thanks to smart, accessible hardware design. The final piece of the design story is scalability: how Hugo grows and adapts over time. Because the system is modular, engineers can add new instruments, imaging devices, or even extra arms without redesigning the base hardware. The software interfaces are built to handle updates, allowing smooth integration of new algorithms or connectivity features. Still, the modularity brings challenges. More components means more cables, coordination, and potential collisions. Each new configuration must maintain predictable behavior, safety, compliance, and intuitive operations for surgeons. To manage this, Medtronic relies on rigorous setup protocols and standardized connectors, balancing flexibility with reliability. Training evolves alongside hardware, with virtual simulations helping teams master docking and calibration. Ultimately, Hugo scalability isn't just about adding features, it's about future-proofing surgical innovation. The architecture anticipates growth, ensuring the system stays relevant and safe as technology and medicine progress.